So in this video, we will show how to represent a number in two complement representation. So in order to express a value into complement representation, there are the two scenario. If the number is positive, just convert it into binary and we are done. On the other hand, if the number is negative, we first need to find a one complement representation of that number, and then we add one to just the one complement representation. Then we get the two complement representation of the number. So here's an example using, for example, we have the 8-bit binary to represent the number 3. In two complement representation, the number 3 that is positive, we just convert into binary and then we are done. So 3 into complement representation equal to 0, 0, 0, 0, 0, 0, 1, 1. Okay, so that's the binary representation of the 3 because this is a positive number. On the other hand, if you want to represent the negative number 3, the first step is that we will find the one complement representation of negative 3. So basically, we first of all represent number value 3. So this one, to get the one complement, we just flip the bit of the positive 3. Okay, so we have the 1 flip the bit gets 0, 1 flip the bit gets 0, and 0 all of the remaining bit right here flip we get 1. Okay, so that's the one complement representation of negative 3. So to represent the negative 3 in two complement, we just add 1 to this one complement representation. So we have the 0 plus 1 equal to 1, and the remaining bit are the same. So we have the negative 3 represented into complement form is as follow 1 1 1 1 1 1 0 1. Okay, so that's the way we represent a number in two complement representation. So with two complement arithmetic, all we do is just add two binary number together and just discard any carry emitting from the high order bit. So here's an example. Assume we using one complement binary arithmetic to find the sum of the 48. I mean this is two complement representation of the 48 and negative 19. So we know that 48 that's the positive number. So in two complement representation, we have the same. So basically here the two complement representation. So the value of the 48 that's represented by this binary string. On the other hand, in order to find the value of negative 19 into complement representation, the first step is that we represent 19 in binary. So we got this string, and then we obtain the one complement representation of the negative 19 by flipping the bit of the 19 right here. So we have the 1 flip the bit, we get 0, 1 flip the bit gets 0, and the do the same for the other bits as well. So we get this string that the one complement representation of the negative 19. So in order to get the two complement representation of negative 19, we just add 1 to the one complement representation of negative 19. So 0 plus 1 equal 1, and the other bit are the same. So I'll just put it 1 right here to get the negative 19. So we get the sum by just adding them together. So we have 0 plus 1 equal 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, gotta be 1, 0, write down 0, carry 1. So 1, 0, 1 equal to 1, 0, write down 0 and carry 1. So 1, 0, 1, write down 0 and carry 1. So in the two complement representation, we just discard 1, and the result gonna be 0 0 0 1 1 1 0 1. Okay, so that's the much simpler compared with the sign magnitude and one complement calculation. We also have the another way to represent the number we call XSM. That's the representation where for the unsigned binary value to represent the signed integer. So the XSM representation is intuitive because the binary string with all 1 represent the smallest number, whereas the binary string with all 1 represent the largest number. Okay, so an unsigned binary integer m called the bias represent the value of 0, and whereas all the 0 in the bit parent represent the integer of 2m. The integer is interpreted as the positive or negative depending on where it falls into the range. So here's a example. The unsigned binary value for the signed integer using XSM representation is determined by simply just adding m to that integer. For example, assuming that we are using the XS7, so the integer value of 0 in decimal representation is represented by a 0 plus 7 equal to 7. So that gonna be in the decimal representation. So 7 gonna be transformed into 0 1 1 1 in binary representation. Okay. Another example, integer 3 in decimal is represented by a 3 plus 7 because we have the XS7, so we just add 7 to that number, we get 10, and then we represent 10 in binary, so we get this string. Okay, so that string represent the number 3 in binary with XS7. How about the number integer negative 7? So basically we do the same, just add negative 7 with 7, we get 0, and then we represent 0 in binary, just the all of bit as equals 0. So how to find the decimal value of a XS7 binary number, for example 1111. So in order to doing that, we just subtract 7 from the result. So basically 1111 in binary we can convert into decimal that's equal to 15. In 15 we subtract 7, we get 8. So 8 is just the value of 1111 in binary in XS7, and value equal to 8 in decimal. Okay. So here's the comparison of different way to represent the number. We have the decimal value in the first column, binary representation of that number. So basically here we don't care about the size. The third column is just a sign magnitude, where we have the first bit right here represent the size of the number, 0 for positive and 1 for negative. One complement representation, the we have the positive number the same, where the negative number just by flipping the bit of the positive number to obtain it, the negative number. The two complement representation, we just obtain the same for the positive number, and we obtain the negative representation by obtain the one complement representation and add 1 to the last digit of the one complement representation to get the two complement representation of a negative number. And XS 127, so basically we add 127 to that number and represent in the binary. Okay, so we can see, for example, number 2 right here, all of the representation gonna be the same. Okay, except the XS7, where 2 plus 127, that's the 129. So this the binary string represent the number 129. Okay, For the -2, we have the binary string is the same. Now for sign magnitude, the first bit right here, that's the represent the sign, that's negative. For the 1 complement, we just flip the bit of this positive 2, so we get the negative 1, the negative 2 in 1 complement. For the 2 complement, we just add 1 to the 1 complement representation, so we have 1 plus 1 equals 0, and we carry 1, so 0 plus 1 equals 1, so the other bits going to be the same. So this is 2 negative 2 in 2 complement representation. Now, for the HZ127, we have the -2 plus with 127, we get a 125. So this bit string represent the value 125. So all are the numbers the same. Okay, so so that's the ways we represent in 2 complement representation in HZM. So when we use any finite number of bits to represent a number, we always run in the risk of the result our calculation become too large or too small to be stored in a computer. So while we can always present overflow, we can always detect the overflow. In complement arithmetic, the overflow condition is easy to detect. Okay, so here the example. For example, using 2 complement binary arithmetic, we find the sum of 107 with 46. So this is 2 positive numbers. So in 2 complement representation, we just use the binary string to represent 2 numbers. So here's the 107, this is 46. So we add them together. 1, 0, this is 1. This 1, 1, this is 1, 0. Write out 0, carry 1. The 1, 1, 0, 1, 0, write out 0, carry 1. 1, 1, 1, that's it, 1, 1, write out 1 and carry 1. So 1, 0, 0 is 1. 1, 1 is a 1, 0, write out 0, carry 1, and 1, 1 is 0 is 1, 0, write out 0 and carry 1. So 1 right here are gonna be a and 0 and 0, that's a 1. So we can see that the non-zero carry from the 7-bit overflow into the side bit, giving us the erroneous result of 107 plus 46. That's the negative 103. Okay, so that's incorrect answer. But the overflow into the side bit does not always mean that we have an error. So here's another example. Using 2 complement binary arithmetic, find the sum of the 23 and -9. Okay, so first of all, we need to represent 23 right here. That's the positive number. That's the same with binary string of the 23. -9. First of all, we compute the we find out the 1 complement of the representation of -9, and then we add 1. So this is the -9 into complement representation. Okay, so to find the sum, we just add them together. 1, 1 is 0, 1, write down 0 and 1, and then so on. Okay, in the last bit right here, we have the 1 carry from the 7th bit to the side bit, and also we have the from the side bit carry out 1 out here. Okay, so we can see that there's a carry into the side bit, and also there's the carry out from the side bits as well. Okay, so 1 carry in for the side bit right here, and 1 carry out from the side bit right here. So the final result is the 23 plus with -9 equals 14. So this actually is the correct one. So we can see that carry out to carry into the side bit not always return an incorrect answer. Okay, so here's the rule for detecting the side to complement overflow. When the carry in and the carry out of the side bit differ, overflow has occurred. if the carry into the side bit equal to the carry out of the side bit, no overflow has occurred. So it means the result in this case is the correct answer. Okay. So the signed and unsigned number are both useful. For example, memory address are always use the unsigned number. Using the same number of bits, unsigned integer can express twice as many positive value as the signed number. Trouble arises if an unsigned value wrap around and for example, we 4 bit 1 1 1 1 plus 1, so we have the overflow just equal 0 0 0. So a good programmer should stay alert for this kind of a problem in order to debug your program.